Right now, the clock on your wrist is running slightly slower than the clock on a satellite in orbit above you. The difference is small, only a few tens of microseconds a day, but it is real and it has been measured. Every clock in the universe runs at its own rate, set by where it sits and how fast it moves. In this video, we are going to follow that idea outward, from the surface of your own planet to the edge of the universe. If the mysteries that reach us from space are the kind of thing you like to sit with, that is what this channel is for, and subscribing is the easiest way to let the next one find you. That is the only such request you will hear. Everything after this is the journey. Begin with something very ordinary. Stand up. The crown of your head is now about 1.5 meters higher above the ground than it was when you were sitting down. That sounds like a nothing of a fact, the sort of thing that has no consequences worth mentioning. But it does have a consequence, and the consequence is that the clock in your head is now running a tiny bit faster than the clock in your feet. It has always been running faster, every time you stood up, every time you walked across a room, every time you climbed a staircase. The cells in your skull age by an infinitesimal amount more quickly than the cells in your souls. Over the course of a human lifetime, the difference works out to a few hundred billionths of a second. It is much too small for any biology to notice, and far too small for any ordinary clock to measure. But it is there, and the most precise instruments humans have ever built can see it directly, across distances much smaller than a person. This is the first hint of the thing that we are going to spend the rest of this video following. The clocks in different parts of you, and in different parts of any object on the surface of the planet, are not synchronized. They never have been. The Earth, despite being one solid object spinning steadily on its axis, does not run on a single time. It runs on many, all very close to one another, all imperceptibly different, and all governed by a rule that we will get to in the next section. For now, the only thing you need to know is that the rule exists and that it makes its presence felt the moment you look closely enough. A few examples of how closely you have to look. In 2010, a team of physicists at the National Institute of Standards and Technology in Boulder, Colorado, raised one of their atomic clocks by 33 centimeters, about the height of a hardcover book, and watched it run faster than its twin on the floor. The difference was about 4 parts in 10 to the 16th, which is to say that the higher clock gained roughly 1 part in 10 quadrillion. Nothing visible happened. Nothing made any noise. The hands of an ordinary watch would not have moved differently by any amount any human could ever perceive. But the comparison between those two clocks, sitting in the same room, separated by the height of a book, was unmistakable. The higher clock was ticking faster, by the exact amount the equations of general relativity predicted, simply because it was 33 centimeters further from the center of the Earth. It is worth taking a moment on what an atomic clock actually is, because the rest of this video depends on the listener trusting that such an instrument can really see what we say it can see. An atomic clock does not have hands, or a pendulum, or a battery in any ordinary sense. It uses the fact that atoms of a particular element absorb and emit light only at very precise frequencies, set by the structure of the atoms themselves. A clock built around an atom of cesium, or strontium, or aluminum counts the natural oscillations of that atom and uses them as the ticks of the clock. The atoms set the rhythm. The clock counts the beats. 2 atoms of the same element anywhere in the universe would oscillate at the same intrinsic rate, so any disagreement between 2 such clocks is not a flaw in the clocks. It is a real disagreement about how time is passing where they sit. This is what makes it possible to talk about 33 centimeters of altitude making a measurable difference. The atoms are not changing. The space they are sitting in is. Imagine what that means about the building you are sitting in. If the floor is on a different clock than the ceiling, then every floor of every building on the planet is running on its own, slightly different time. A high-rise office tower in Tokyo or New York has clocks at the top that are gaining microseconds over years on the clocks at the bottom. The receptionist in the lobby and the executive in the corner office on the 40th floor are not actually living in the same moment by the standards of an instrument precise enough to notice. The discrepancy is much too small for any decision to depend on, but it is not zero. It is what the universe is doing, continuously, everywhere. Step outside. Walk to the foot of a mountain. The summit is several kilometers above you, and the clocks on the summit are running faster than the clocks at the base by something close to a part in a trillion. A mountaineer who spends 2 months on a Himalayan peak returns to sea level very slightly older than they would have been if they had stayed home, by an amount measured in nanoseconds. The difference is the same effect, scaled up. Standing on a mountain puts you a little further from the center of the planet, and the clocks at that higher position tick faster than the clocks at the lower one. Now look at a body of water. The ocean is not strictly on the same clock as the shore, because the surface of the ocean is at a slightly different distance from the Earth's center than the surface of the land. The oceans have been carefully mapped to centimeter-level accuracy, and any genuine measurement of time across the planet has to account for the height of the ocean's surface as well as the height of the continent. The difference is, again, tiny, but it is part of how the modern world works. The clocks that maintain the international standard for time are spread around the planet at known altitudes, and their readings are continuously corrected for the gravitational time dilation between them before being averaged together. Without those corrections, the international second would drift between countries, and the modern infrastructure of navigation, communication, and finance would slowly lose its agreement about what time it is. Then look up. The satellites in low Earth orbit, the kind of orbit used by the International Space Station and by most weather satellites, sit a few hundred kilometers above the surface. Their clocks run faster than ours by a few tens of microseconds a day, on account of being higher in the Earth's gravitational well. They also run slower, by a smaller but still significant amount, on account of moving much faster than we do. The two effects, gravity and motion, push in opposite directions, and we will come back to both of them in a later section. The point for now is that the satellites overhead, the ones that broadcast position signals to your phone, are not on the same clock as the ground stations that listen to them. The difference between the two clocks is not a flaw in the system. It is corrected continuously, every second, by the engineers who built the system. Because if it were not corrected, the position your phone reports would drift off by kilometers within hours. Higher still, the satellites in the medium Earth orbits used by global positioning, about 20,000 kilometers up, run even faster than those in low Earth orbit, because they sit even higher in the Earth's gravity well. Higher still, at 36,000 kilometers, the geostationary satellites that carry television broadcasts and certain communication signals run faster yet. And the Moon, 400,000 kilometers out, is on a clock that gains roughly 50 microseconds per day on the clocks of the surface of the Earth. The lunar samples brought back by Apollo astronauts in the 1960s and 70s are not, in a very technical sense, the same age as identical rocks left undisturbed on the Earth. They have aged slightly faster because they spent their geological lifetimes on a body with weaker surface gravity than ours. The effect is far too small to matter for any geological or chemical purpose. It is large enough to be calculated. It is real. The pattern at this point should be visible. The higher you go, the further you are from the center of the planet's gravity, the faster your clock runs. And the faster you move, the slower your clock runs. Every point on Earth, every satellite around it, every spacecraft we have launched, every body in the solar system, is on its own clock. Some of them are very close to ours. Some of them differ by tiny amounts. None of them is exactly synchronized with any other. This is what the universe looks like when you accept that there is no single clock. It does not look strange in any sudden theatrical way. There are no obvious paradoxes that present themselves in ordinary life. A century ago, before atomic clocks existed, none of these effects could be measured at all. We lived our whole history in a universe with no single clock and never noticed, because the differences between any two clocks on Earth were always far smaller than any clock we possessed could detect. The wristwatches and pendulums and church bells of the ancient and medieval world all agreed with one another to the precision of those instruments, and so the universe presented itself as a place with a single time that ticked the same everywhere. The discrepancies were buried in the digits no clock could resolve. What changed in the 20th century was the precision of the instruments. Atomic clocks reach an accuracy that in modern versions would gain or lose less than a second over the age of the universe. Once a clock that good exists, the small disagreements between locations on Earth become impossible not to see. The clock in Boulder, Colorado, sitting at an altitude of 1.5 kilometers, runs measurably faster than the clock in Paris at the standard meter above the sea. And the international system has to apply a small daily correction to keep them in agreement. The clock at the United States Naval Observatory in Washington, sitting at a different altitude and on a slightly different rotational speed, has to be corrected against the others as well. None of them, by themselves, gives the right answer for what time it is in any other place. They give the right answer for their own location, and the system as a whole computes a kind of weighted average. There is no clock you can carry, no matter how precise, that will tell you what time it is anywhere except where it sits. There is no master clock of the universe to which any of them could be compared. The picture of time that everyone walks around with, in which a moment is simply a moment, the same for everyone everywhere, is an approximation that works in ordinary life and breaks down the instant we begin to measure carefully enough to see what is actually there. In the rest of this video, we will leave the surface of the Earth and see how this gets stranger. The clock on a satellite is one thing. The clock on a probe diving toward the sun is another. The clock on a pulsar that spins 700 times a second is another still. The clock on a star whipping around a supermassive black hole is something else again. And the clock of an entire galaxy, billions of light years away, whose light has been climbing toward us for so long that the very seconds of its supernovae have stretched as they cross the expanding universe, is something we may not yet have a comfortable language for. By the end of this video, we will have seen each of them. To get there, we have to take a short detour into the reason any of this is true. The differences between clocks on different floors, the speed up of satellites overhead, the slowing of moving particles, the stopping of time at the edge of a black hole. All of these are consequences of two ideas that a single person came up with in the first 2 decades of the 20th century. We do not need the full theory to follow what time is doing in the universe. We need only the heart of the argument, the part you can understand without any mathematics at all, that the speed of light is the same for every observer no matter how they move, and that gravity is not a force pulling things toward heavy objects, but a curvature of the very fabric that time and space are made of. From those two ideas, all the strangeness that follows can be derived. We will spend the next section on them, briefly, so that the rest of the video can let the universe speak for itself. The story begins, as so many stories in modern physics do, with light. Light has the peculiar property of traveling at a single fixed speed, about 300,000 kilometers per second in vacuum. And at the very end of the 19th century, a series of careful experiments established something extraordinary about that speed. It does not depend on who is measuring it. A beam of light passing the Earth is measured to be traveling at 300,000 kilometers per second by an observer on the Earth, and it would be measured at exactly the same speed by an observer on a passing spacecraft, regardless of how fast that spacecraft was moving. This contradicts everything ordinary experience tells us about speeds. A ball thrown forward from a moving car travels, relative to the road, at the speed of the throw plus the speed of the car. Light does not obey that rule. The speed of light, as measured by any observer in any state of motion, is always the same number. This was an enormous and unsettling fact, and in 1905, a 26-year-old patent clerk in Bern named Albert Einstein took it seriously. He asked what the universe would have to look like for that fact to be true, and the answer turned out to be that time could not be the same for every observer. If two clocks were moving relative to each other, they could not, by the geometry of the situation, agree about how much time was passing. The faster one of them moved relative to the other, the more slowly it would appear to tick when viewed from the other's frame of reference. The slowing was small at ordinary speeds, but it grew without limit as the moving clock approached the speed of light itself. This is the phenomenon called time dilation, and it was the central consequence of what came to be known as the special theory of relativity. The argument for it can be made with a thought experiment, and the thought experiment is short enough to walk through. Imagine a clock built on a simple principle. Two mirrors face each other, with a flash of light bouncing between them. Each round trip of the light from one mirror to the other and back counts as one tick of the clock. Because the speed of light is fixed and the distance between the mirrors is fixed, the rate at which this clock ticks is perfectly determined. No real clock is built this way, but any clock could in principle be analyzed as if it were, because all clocks ultimately measure time by counting something that oscillates. Now place one such clock in a laboratory and another, identical, inside a spacecraft passing at some substantial fraction of the speed of light. To an astronaut inside the spacecraft, sitting next to the clock she is carrying, that clock behaves entirely normally. The light flash bounces straight up and down, completing its round trips at the expected rate. To an observer in the laboratory, however, the spacecraft is moving past. And so the flash of light inside the spacecraft, during the time it takes to travel from one mirror to the other, must also be carried along sideways with the spacecraft. The path the laboratory observer sees the flash take is a diagonal, longer than the up and down path the astronaut sees. But the speed of light, by the central principle, must be the same for both observers. The same flash, in the same one tick, must cover a longer distance from the laboratory's perspective at the same speed. The only way that can be true is if the tick, as measured by the laboratory observer, takes a longer time than it does as measured by the astronaut. A clock whose ticks take longer is a clock that is running slow. The moving clock, as seen from the laboratory, is ticking more slowly than the clock at rest. The clock is not malfunctioning. The mirrors are not warped. The light is not delayed. No mechanism inside the apparatus is misbehaving. What has changed is the rate of time itself for the moving frame. This is what motion does to time by the geometry of the situation, the moment we accept that the speed of light is a constant. The amount of slowing depends on the speed. At ordinary human speeds, on a freeway or on a passenger jet, the effect is so small as to be invisible. At the speed of the International Space Station, about 8 kilometers per second, an astronaut ages roughly 25 microseconds per day more slowly than the ground crew below. At the speed of a particle in a laboratory accelerator, very close to the speed of light, a moving clock can run at less than 1/100th the rate of a stationary one. At the speed of light itself, which no material object can ever quite reach, the formal slowing would become infinite, and time would, in some sense, stop. Light itself in this picture experiences no time at all. A photon emitted by a distant star and absorbed in your eye from its own perspective takes no time whatsoever, no matter how many billions of years the journey took as measured by anyone else. That is the first idea. The second one is gravity, and it took Einstein another decade to work out. Special relativity, his 1905 theory, applies to observers moving at constant speeds in straight lines. It says nothing about acceleration and nothing about gravity. Newton's gravity, the picture that had stood for 200 years, treated gravity as a force reaching instantaneously across space. The same way Newton's time was the same everywhere at once. Einstein, who had just dismantled the second of those assumptions, knew he would eventually have to dismantle the first as well. The weigh-in came in 1907, when Einstein noticed something so obvious that no one had thought to make a theory out of it. A person falling freely does not feel their own weight. This sounds trivial, but Einstein turned it into the equivalence principle. He imagined two sealed rooms with no windows. One room sits at rest on the surface of a planet, and a person inside it stands on the floor with their normal weight. The other room sits far out in empty space, attached to a rope that pulls it upward so that it accelerates steadily. The floor of the second room rushes up to meet the person's feet, pressing against them with exactly the same force the planetary floor presses with. Inside the sealed rooms, Einstein argued, no experiment could distinguish the two situations. The pull of gravity and the push of acceleration are, in any local measurement, the same thing. This single equivalence, taken seriously, forces a conclusion about time. Imagine a clock on the ceiling of the accelerating room and another on the floor. The ceiling clock sends down regular pulses of light. While each pulse is in transit, the floor of the room is accelerating upward to meet it, so the floor receives the pulses at a higher rate than the ceiling is sending them. The floor sees a faster tick rate. From the floor's perspective, the ceiling clock is running slow. And because acceleration and gravity are equivalent, the same thing must happen in any room sitting in a gravitational field. A clock higher up runs faster than a clock lower down. A clock further from a heavy object runs faster than a clock closer to it. It took Einstein 8 years to embed this insight in a complete theory of gravity, and the resulting picture, completed in 1915, replaced Newton's invisible force with something stranger and more visual. Mass and energy curve the very fabric of space and time around them. The Earth's mass puts a long, smooth valley into that fabric. The Sun's mass puts a deeper one. A black hole puts a shaft so deep that the fabric closes around itself. And what we feel as the pull of gravity is simply the natural tendency of any moving object to follow the shape of the curved fabric, the same way a marble rolled across a stretched sheet of rubber rolls toward any heavy ball resting on it. Gravity is not a force. It is geometry. The rubber sheet image is useful and also slightly misleading because it explains gravity using gravity. The ball sinks because the Earth is pulling it down into the sheet. So hold it loosely. What the image gets right is the essential idea. Mass and energy do not reach out and grab. They tell the space around them how to curve, and that curved space tells everything moving through it how to travel. The Earth orbits the Sun not because a rope of force connects them, but because the Sun has carved a deep, smooth valley into the shape of space, and the Earth is rolling around the inside of that valley along the straightest path available to it. A falling apple is following the curvature of space caused by the Earth's mass, on the straightest path available to it through the curved geometry. There is no pulling. There is only the shape of things, and motion following the shape. In that geometry, time is one of the 4 dimensions of the curved fabric. The fabric is called space-time because space and time are woven together in it, and a clock placed anywhere in the universe is following a path through space-time, whose length, measured along that path, is the time the clock records. A clock sitting deeper in a gravitational valley follows a path through space-time that, by the geometry of the curved region, is shorter than the path of a clock sitting higher up over the same interval. Less path means less time, so the lower clock records less elapsed time than the higher one. Gravity slows time by the same logic, ultimately, that bends light around the sun. That is all the theory the rest of this video really requires. Two ideas, both due to Einstein, both confirmed in countless experiments since they were proposed. Motion slows time. Gravity slows time. The first effect depends on the speed of the moving clock relative to whoever is watching it, by a factor that becomes dramatic only at speeds approaching the speed of light. The second effect depends on how deep in a gravitational field the clock sits, by a factor that becomes dramatic only near very massive, very compact objects. In the everyday world, both effects are tiny. In the universe at large, both effects are sometimes enormous. The two effects are not separate phenomena exactly. In Einstein's full theory, they are aspects of one underlying picture, in which the geometry of space-time is shaped by the mass and energy within it, and clocks everywhere follow that geometry. But for the purposes of this video, it will be useful to think of them as two distinct levers, one called motion and one called gravity, both of them capable of bending the rate at which time passes. We will meet places in the universe where only one of the levers is at work, and places where both are, and places where the effects of both are so extreme that the very notion of what time it is loses its ordinary meaning. One last thing to say before we leave the theory behind, because it bears on what follows. The slowing of moving and deep-sitting clocks is not a matter of the clock somehow malfunctioning under stress. It is not a mechanical effect. It is what time itself is doing in those places. A muon moving at nearly the speed of light through a particle accelerator is not, in any meaningful sense, an ordinary muon whose internal workings have been disturbed by its motion. From the muon's own perspective, nothing whatsoever is wrong, and nothing is slowed. The slowing exists only as a fact about how the muon's time compares to the time of the laboratory. Two observers in different states of motion, or at different depths in a gravitational field, will simply disagree about how much time has passed between any two events, and both of them, in their own frames, will be correct. This is the heart of what it means to say that the universe has no single clock. There is no master rate against which the others can be compared. There is only the time recorded by each particular clock in each particular place, set against the geometry of the space-time it occupies. To find out what time it is anywhere, you have to ask the clock that is actually there. Any answer you get from anywhere else is, strictly, a calculation, not an observation. With the theory in hand, we can now leave it behind. The rest of this video will not, for the most part, be about Einstein or about equations. It will be about places. Places on the planet, places in the solar system, places near stars and the remnants of stars, places at the edges of black holes, places far enough away in the universe that the light from them is older than the planet we are watching it from. Each of those places has its own clock, ticking at its own rate, set by where it is and how it moves. We will visit them in order, beginning with the planet beneath us and ending with the moment at the start of the universe itself. The planet beneath us is, by the standards of the cosmos, a quiet place. It is small in the universal scheme, just under 13,000 kilometers across, and the gravitational valley it carves into space-time is shallow compared to almost any other object we will visit. The slowing of time at the Earth's surface, relative to a clock infinitely far from the planet, comes out to about 7 parts in 10 billion. This means that for every second that passes on a clock far from any gravitational influence, a clock on the surface of the Earth ticks roughly 7 nanoseconds less. In a single human life, the discrepancy accumulates to about 1.5 seconds. We are, all of us, that much younger than we would have been if we had spent our lives drifting in interstellar space. The universe, when it eventually comes to weigh up what time it is here, will find us a second or two behind. And yet, in this quiet place, the unevenness of time is everywhere. Sit still for a moment and consider what is going on around you. The clocks at the summit of Mount Everest, 8.5 kilometers above the sea, are running faster than the clocks in your room by about 30 microseconds per year. The clocks at the bottom of the Mariana Trench, 11 kilometers below the surface of the Pacific, are running slower than yours by about 40 microseconds per year. The clocks at the centers of the Earth's deepest oil and mineral mines, 3 or 4 kilometers down, are slower than the surface by amounts you can calculate but never feel. The interior of the planet is on a clock measurably different from its exterior. The molten iron and nickel of the outer core, slowly churning beneath your feet, has been ticking this whole time at a rate slightly behind ours. Even within the rooms of an ordinary building, the inequality is there. We met this in the previous section, but it is worth dwelling on, because the more carefully one looks, the stranger the planet's relationship to time appears to be. The clock at the top of a high-rise office tower, 400 meters above the lobby, gains roughly a nanosecond per month on the clock at the bottom. A child playing on the top floor of such a building is aging, by an infinitesimal but real amount, more quickly than a child playing in the basement. If two friends spend their 20s in different cities, one in the Andean highlands at 3,000 meters and the other on the coast at sea level, the highland friend will, by the end of their 30s, have lived about 10 microseconds longer than the coastal one. These differences are far below anything biology could register, or any ordinary instrument could see. But they are there, and the most precise clocks of our century can measure them across surprisingly short distances. The clocks that can do this are extraordinary instruments. The International Standard of Time, which defines the second, is maintained by atomic clocks based on a particular transition in the cesium atom. The clocks currently used in primary timekeeping laboratories around the world, in Paris and in Boulder and in Tokyo and in Braunschweig, and in a dozen other locations, are accurate to within about 1 part in 10 to the 16th, or 1 second every 300 million years. The newer generation, called optical lattice clocks, use heavier atoms cooled almost to absolute zero and trapped in patterns of crisscrossing laser light. These can reach accuracies of 1 part in 10 to the 18th, which is to say they would gain or lose less than a second over the age of the universe. With clocks that good, the warping of time across a single tabletop becomes routinely measurable. A team at the Japanese Metrology Laboratory in 2020 reported a comparison between 2 optical clocks separated by 450 meters of altitude on the Tokyo sky tree. The lower clock ran slower than the upper by exactly the amount Einstein's theory specified, with no adjustment, to 4 decimal places. The sky tree is a broadcasting tower built for ordinary purposes, and what they were measuring was the curvature of spacetime across its height. The planet's clocks, taken as a whole, do not synchronize themselves. They have to be synchronized by hand, or rather by computer, every second by an international system whose purpose is to maintain something called coordinated universal time. The system pools the readings of about 400 atomic clocks around the world, weights them by their stability, and combines them into a single official rate. Each contributing clock has its altitude measured to centimeter precision, because that altitude determines how much faster or slower it is running than the international average. The corrections are applied silently, in software, and the result is a single official time that no actual clock anywhere on Earth keeps directly. It is a kind of fiction, a consensus rate that everybody agrees to use, knowing that their own clock is not quite ticking at that rate. The very moment-by-moment ticking of human civilization has, since the 1960s, depended on continuously correcting for the fact that no 2 places on Earth share a single time. This sounds abstract until you consider what depends on it. The financial markets, in which trades are now sometimes executed in microseconds, would lose their agreement about the order of events if the clocks at the major exchanges were not synchronized to within hundreds of nanoseconds of each other. The electrical grid, which has to phase the alternating current it delivers to within a tiny fraction of a cycle across hundreds of kilometers of transmission lines, requires the same kind of agreement. The telephone networks, the data centers that route the internet, the navigation systems we will come to in a moment, all of them are riding on a constantly maintained accord between clocks that are, in fact, all ticking at slightly different rates because of where they happen to sit. Now lift your gaze. A few hundred kilometers above your head, the International Space Station completes another orbit. It travels at roughly 8 kilometers per second, fast enough to cross the United States in 7 minutes, and the people inside it experience their motion as steady, weightless drift. There are usually 6 or 7 astronauts on board at any given time. They live there for months, sometimes for a year, and every second they spend up there, they are aging more slowly than they would on the ground, by an amount that is now measured routinely. The motion-based slowing dominates at that altitude, because the orbit is fast and not very high. The gravitational speedup partially offsets it, but only partially. The net effect is that an astronaut who spends 6 months on the station returns to Earth about 7 milliseconds younger than the calendar would suggest. They have, in a strict and measurable sense, time traveled into the future of their twins on the ground by 7 milliseconds. This sounds like nothing, and in any practical sense it is nothing. 7 milliseconds is far less than the blink of an eye, but it is real, and we have confirmed it directly. In 2015, the American astronaut Scott Kelly spent 340 days continuously on the station, while his identical twin brother Mark, also an astronaut, remained on the ground as a kind of biological control. When Scott returned, he was about 5 milliseconds younger than Mark, by the clocks they had been comparing against. The brothers had begun their lives at the same moment. They had ended a year of separation at slightly different points along the universe's accounting of time. It is the closest thing to a controlled experiment on human aging across reference frames that anyone has ever managed. What is most worth noticing about the Kelly experiment is not its size, but its asymmetry. The two brothers did not merely see each other's clocks running slow during their separation, in the way that two observers passing each other in spacecraft would, with each one's clock looking slow to the other and no fact of the matter about who was really aging less. Scott genuinely came back younger than Mark, by a definite amount that everyone agrees on. The reason for the asymmetry is that Scott did not move in a straight line. He went up to the station, accelerated into orbit, circled the planet for a year, and then decelerated to land. Mark stayed in one place. In Einstein's geometry, the path Scott took through spacetime was a longer, more curved path than Mark's, and a longer, more curved path corresponds to less time accumulated. Two clocks that begin at the same place and meet again at the same place can disagree about how much time has passed between those meetings, and the one that traveled the more roundabout path will always show less. This is what biology actually does to twin astronauts. It is also, in a much more extreme form, what biology would do to interstellar travelers, who could return to find that their friends had been dead for centuries, while they themselves had aged only a few years. The mechanism is the same. It is just the scale that differs. The orbiting astronauts are still only barely above us by cosmic standards. The satellites of the Global Positioning System are much higher, 20,000 kilometers up. They circle the Earth twice a day, moving at about 14,000 kilometers per hour. They are too high for the velocity effect to dominate. The gravitational speedup wins, and the satellite clocks gain time on the ground clocks at a rate of about 38 microseconds per day. 38 microseconds per day is enormous by the standards of a navigation system, because a positioning error of 1 nanosecond corresponds to a positional error of about 30 centimeters. After a single day of uncorrected drift, your phone would think you were nearly a dozen kilometers from where you actually are. After a week, it would not know which continent you were on. The engineers who designed the system in the 1970s knew this, but the knowledge sat uneasily with them. There were people on the project who genuinely did not believe relativity was real enough to put into satellite hardware. The first GPS satellite, launched in 1977, carried clocks with a switchable correction. The hardware was set up so that the relativistic adjustment could be turned on or off from the ground, partly as an engineering convenience, and partly because the senior managers wanted the option of running the satellite without it, to see what happened. What happened was that the satellite clocks immediately began to drift, exactly as Einstein had predicted. And within hours, the engineers turned the correction on and left it on. Every GPS satellite launched since then has carried the relativistic correction baked into its operating software from the day of launch. Without those corrections, the system would be useless. With them, it can place you on the planet to within a few meters, every time, anywhere, day or night. There is something quietly moving in this. The phone in your pocket is, every time you ask it where you are, performing a calculation that depends on accepting Einstein's two theories of relativity as accurate descriptions of how the universe really works. The agreement is not metaphorical. It is to many decimal places, every second of every day, in a system that millions of people use without ever knowing why it works. The slowing of moving clocks and the speeding of high-altitude clocks have become, in the 21st century, a piece of consumer infrastructure. Every airline flight, every shipping container tracked across an ocean, every package delivered, every car routed through a city, every emergency dispatched to a calling phone, is riding on the corrected timing of satellites whose clocks tick at a rate Einstein worked out by thinking about light beams in sealed rooms. The Earth itself, taken as a whole, is on a clock that nothing in the system measures directly. We measure individual locations and then correct between them. The official time of the planet is a kind of distributed agreement, a continuously updated average of clocks that disagree by amounts everyone has learned to compensate for. Far above all of this, the Moon orbits, on its own clock that we have already noted, runs about 50 microseconds per day ahead of the ground. The Moon has been our companion for 4.5 billion years, and through every one of those years, it has been keeping a slightly different time than we have. The lunar surface, in its long quiet, has aged about 1.5 years more than the surface of the Earth by the strict accounting of general relativity. The samples brought back by the Apollo astronauts are, in that strict sense, slightly older than the Earth rocks they were compared against. The difference is far too small to affect any geological measurement, but it is part of how the solar system actually keeps time. Beyond the Moon, the next major object is the Sun. And there the gravitational well begins to deepen in earnest. The Earth lies 150 million kilometers out from the Sun. And at that distance, the Sun's gravity makes a noticeable, though small, contribution to how our clocks run. As we move inward toward the Sun's surface, the gravitational slowing grows. By the time we reach the photosphere, where the visible light of the Sun is emitted, the slowing has become large enough to be seen in the colors of the light itself. To follow what time is doing in the solar system, we have to leave the planet, and the first thing we will encounter on the way out is a star. The Sun is, by every reasonable standard, an ordinary star. It is a yellow dwarf of medium mass, slightly heavier than average among the stars in our neighborhood, on the long, stable main phase of its life. There are roughly 400 billion stars in our galaxy alone, and most of them are smaller and dimmer than this one. The Sun has been shining steadily for 4.5 billion years, and it has roughly the same again left in it before its hydrogen fuel runs out. Among the objects we will visit in the rest of this video, it is one of the most placid, and yet it is, by an enormous factor, the deepest gravitational well in our solar system. The mass of the Sun is about 330,000 times the mass of the Earth, packed into a sphere 110 times wider, and the curvature of space-time around it dominates everything happening in our neighborhood of the galaxy. A clock at the surface of the Sun, in the photosphere where its light is emitted, runs slow compared to a clock at the Earth's distance by about 2 parts in a million. This is not a number that means much in the abstract, so consider what it implies in practice. Over the 4.5 billion years the Sun has been shining, its surface has aged about 9,000 years, less than the empty space at the Earth's orbit has. The interior of the Sun, deeper still in the gravitational well, has aged less yet, and every photon of sunlight reaching us, every grain of warmth on a summer afternoon, has been climbing up out of that valley before it ever set out on its 8-minute journey to our atmosphere. As the light climbs, it loses energy, the way any object loses energy when climbing against gravity. And although it cannot slow down, because its speed is fixed, it can become a little redder. The colors of sunlight arrive at the Earth measurably shifted, by about 2 parts in a million, toward the red end of the spectrum, compared to what they would be if the Sun were not deep in its own gravity well. This is called gravitational redshift, and it is the direct visible counterpart of the slowing of the Sun's clock. The shift is small, 2 parts in a million, but it has been measured many times over the past century in spectral lines of various atoms in the solar atmosphere. The earliest measurements, made in the 1920s, were too crude to give a clean answer, and there was a stretch of years in which the predicted shift in the Sun's light was one of the more controversial pieces of evidence for general relativity. The modern measurements, made with high-resolution spectrometers comparing the same atomic transitions in the Sun and in laboratory sources on Earth, agree with Einstein's prediction to better than 1 part in 10,000. The Sun, in its long, quiet morning, is shining at us with light that has been slowed and reddened by its own gravity, exactly as the theory says it should be. Move now to the surface of one of the planets. Mercury, the closest to the Sun, orbits at about 1/3 of the Earth's distance from it, and at that depth the Sun's gravity slows clocks meaningfully, more than at Earth's distance. A clock on Mercury runs slow by about 3 times the Earth's rate of slowing, attributable to the Sun. Mercury also moves much faster in its orbit than the Earth does, completing 1 revolution every 88 days at an average speed of nearly 48 kilometers per second. So the velocity effect adds further slowing. Both effects combined make Mercury one of the slowest clocked surfaces in the solar system, after the surface of the Sun itself. Over the 4.5 billion years of the solar system's existence, the surface of Mercury has aged about 700 years, less than the surface of the Earth has, by the accounting of general relativity. This is small by cosmic standards, but it is not nothing. If a civilization had been keeping a careful clock on Mercury since the planet first cooled, it would now be measurably out of step with a clock kept on Earth, by an amount that any decent instrument could resolve. Venus is closer to the Earth in time because it orbits at about 3/4 of the Earth's distance from the Sun and at a similar speed. Mars, further out, has aged slightly more than the Earth in cosmic time, by an amount close to the Earth's own slowing, but slightly less. The asteroid belt, further still, runs faster yet. By the time we reach the outer solar system, the gravitational pull of the Sun has become weak enough that the surfaces of the giant planets are ticking at rates much closer to that of empty space, with only their own self-gravity slowing them. The clouds at the top of Jupiter's atmosphere have aged about 1 minute more than the surface of the Earth has over the course of the solar system's life. The icy moons of Saturn, further still, have aged a few minutes more than Jupiter's clouds. Pluto, at the outer edge of the planetary region, has been ticking at a rate so close to that of free space that the difference accumulated over 4.5 billion years comes to only some hours. This is how the solar system actually keeps time, when you look at it carefully. Every body has its own clock, set by its own depth in the Sun's gravitational valley, and by its own speed of motion. The bodies do not synchronize. They have never synchronized. Over the long history of the system, the inner worlds have lagged behind the outer ones by amounts that grow slowly but steadily, until the present moment, when the lag from Mercury to Pluto is measured in centuries. We have, over the past 60 years, sent a number of spacecraft out into this system, and every one of them has been on its own clock, drifting against the Earth's by amounts the engineers have had to track to keep the missions working. The two Voyager probes, launched in 1977, have spent nearly half a century in flight. Voyager 1 has reached interstellar space, about 24 billion kilometers from the Sun at the time of this recording. Voyager 2 is not far behind. Both of them are climbing out of the Sun's gravity well at high speed, and so both of their clocks are doing two things at once. They are gaining time by being higher in the Sun's well than the Earth is. They are losing time by moving faster than the Earth does. The two effects are small at the Voyager's speeds, which are still less than 1/10,000th the speed of light. But the engineers at the Jet Propulsion Laboratory in Pasadena have tracked them for decades. And the predictions of relativity have held in every comparison. The Voyagers carry, on their golden records, recordings of human voices and music, intended in principle for any other civilization that might one day encounter them. The recordings, by the clocks of the spacecraft, have been playing in the silent dark for 47 years. By the clocks on Earth, the same period is about 1.5 seconds longer, owing mainly to the velocity slowing of the moving spacecraft. The discrepancy is unimaginably small in proportion to the journey, but it is real, and it grows as long as the Voyagers continue to coast. There is something quietly poignant about this. The recordings on the Voyager's golden records contain greetings in 55 human languages, the sound of a kiss, the song of a humpback whale, an electrocardiogram, and selections of music ranging from Bach to Chuck Berry. None of those recordings has finished playing. They are traveling outward, on their own clock, a few seconds out of step with the Earth, and they will continue to drift further out of step for as long as the probes have power. By the time the gold-plated copper of the records has degraded into uselessness, billions of years from now, the spacecraft will have aged measurably less than the empty space they are passing through. They are, in a small and strict way, time-traveling into the universe's future by an amount that grows every year. A more dramatic case is the Parker Solar Probe, launched in 2018, which is currently the fastest object humans have ever built. Its mission is to dive repeatedly toward the Sun, threading the upper atmosphere of the star to study how the corona is heated. At its closest approaches, called perihelion, the probe travels at about 200 kilometers per second, the highest speed any human-made object has ever reached. It also passes deeper into the Sun's gravity well than any of our other spacecraft. At perihelion, the Parker probe's clock runs slow against Earth's by something like 1 part in 3 million, accumulating measurable lag over each pass. The probe makes one of these passes every few months. By the end of its planned mission, the probe will have aged appreciably less than the engineers on the ground tracking it, by amounts they monitor as a routine part of running the spacecraft. The same considerations apply to every other probe we have sent out. The two Pioneer spacecraft, the 4 Mariners, the Cassini orbiter that spent 13 years circling Saturn, the New Horizons probe that passed Pluto in 2015, the half-dozen rovers that have crawled across the surface of Mars, the Juno spacecraft now orbiting Jupiter, all of them have been on their own clocks, ticking at rates Einstein's theory specifies and the engineers continuously account for. None of these clocks agree with the clocks on Earth. None of them agree with each other. The solar system is a region in which dozens of small atomic clocks on dozens of spacecraft drift continuously against the ground. The most extreme case so far has been the Bepi-Colombo probe, on its way to Mercury, which has been using a series of gravity-assist flybys of the Earth and Venus to bend its trajectory toward the inner solar system. During those flybys, it has come within a few hundred kilometers of these planets at relative speeds of many kilometers per second, briefly placing it deep in their respective gravitational wells. The engineers have had to model the time dilation along every meter of the trajectory in order to keep the radio communications synchronized. They do so with software that bakes in both special and general relativity, and the model agrees with the measured radio signals to far better than the precision needed to maintain contact. A particularly clean kind of measurement happens every time one of our spacecraft passes behind the Sun, in what astronomers call a superior conjunction. As the spacecraft swings around the far side of the Sun, the radio signals from it have to climb in and out of the Sun's deep gravity well to reach the Earth. The signals do not bend much, but they slow by a measurable amount as they cross the curved space near the Sun. The slowing was first predicted by the American physicist Erwin Shapiro in 1964 and confirmed shortly afterward with radar signals bounced off Mercury and Venus when those planets were near the far side of the Sun. The delay for a signal grazing the Sun's edge is about 240 microseconds. The Cassini probe, while it was at Saturn in 2002, was used to test this effect to the highest precision ever achieved, confirming general relativity's prediction to better than 20 parts in a million. Every time a deep space probe disappears behind the Sun from the Earth's point of view, the engineers tracking it know that the signal will be subtly delayed, and they take the delay into account, because the curved space around a star is real enough to measure with a radio receiver. Underlying all of this is something that bears repeating, because the more carefully one watches, the more remarkable it becomes. The solar system is not, in any literal sense, a single thing keeping a single time. It is a collection of bodies and instruments, each one on its own clock, drifting against one another in patterns determined entirely by where they sit in the Sun's gravity and how fast they are moving. The motion and the gravity together determine the rate at which each clock ticks, and the rates are all slightly different, and the differences are real and measured. Every photograph of Jupiter that has ever been beamed back to Earth was taken on a camera whose internal clock was, at the moment of the shutter, ticking at a slightly different rate than the clocks at the receiving stations. Every command sent out to a Mars rover has had to be timed to arrive when the rover's own clock said it should. None of this is exotic engineering. It is the routine consequence of operating in a region where time is not a single thing. So far, the slowings we have encountered have been small. A clock on the Sun's surface running slow by 2 parts in a million is not, by cosmic standards, much. We have stayed in the gentle outer regions of what gravity is capable of doing to time. But the universe contains objects whose gravity is, by comparison, ferocious. They are dead stars, the burnt-out remnants of stellar furnaces that ran out of fuel and collapsed inward upon themselves, and around them the slowing of time is no longer measured in parts per million. It is measured in tens of percent. To see what time looks like there, we have to go to the graveyards of stars. A star, while it is alive, is a struggle. Its own gravity, the weight of all that gas pressing inward, would crush it to a point in minutes if nothing pushed back. What pushes back is the heat and pressure of nuclear fusion in the core, where hydrogen atoms are fused into helium and prodigious quantities of energy are released. That outflowing energy generates the pressure that holds the star up. For as long as the fuel lasts, gravity and pressure stand in tense equilibrium, and the star shines. Our Sun has been doing this for 4.5 billion years, and it has roughly the same again before it has to stop. But the fuel does run out. Eventually, a star uses up the hydrogen in its core, and then, depending on its mass, the helium that fusion produced, and then heavier elements still, working through a periodic table of energy sources, each harder to ignite than the last. With each stage, the outward pressure flickers and shifts, and the star swells, contracts, and sheds layers in great slow gasps. The Sun, when its turn comes, will swell into a red giant, large enough to swallow Mercury and Venus, and probably the Earth, then puff its outer layers away as a glowing shell into the surrounding space. What remains will be the burnt-out core, dense, hot, and silent. That core is the first of the objects we will visit in this section. It is called a white dwarf. A white dwarf, when one of our sun's mass finishes collapsing into it, is about the size of the Earth, a sphere only about 13,000 kilometers across, but containing very nearly the full mass of the star that produced it. The density is staggering. A teaspoonful of white dwarf matter would weigh several tons on the surface of the Earth. The surface gravity, where the visible material sits, is roughly 100,000 times that of our planet. Time, on the surface of such an object, runs about 3 parts in 10,000 slower than time far away. This is a slowing factor, more than 100,000 times what we see on the surface of the Earth, but it is small compared to what we will encounter shortly. The first white dwarf identified was the small companion of the brightest star in our night sky. Sirius, in the constellation Canis Major, was seen as far back as antiquity to be the brightest pinpoint of light visible from Earth at night. And through the 19th century, it was found to wobble subtly across the sky in a way that indicated an unseen companion. That companion, called Sirius B, was eventually photographed and found to be tiny, hot, and white, sitting in a tight orbit with the larger and brighter Sirius A. Its mass was about that of the Sun. Its size was about that of the Earth. The density implied was staggering. Astronomers in the early 20th century had to be reluctantly persuaded that such matter could exist at all. The slowing of time at the surface of Sirius B was predicted by general relativity to produce a visible redshift in its spectrum, similar to what we see in the Sun's light, but much larger, because the surface gravity is so much higher. In 1925, the American astronomer Walter Adams, working at the Mount Wilson Observatory, made the first measurement of this redshift in the spectrum of Sirius B, and reported a result consistent with Einstein's theory. The measurement had problems, as we noted earlier, but later measurements with better instruments confirmed it. The light from Sirius B reaches us at frequencies shifted by about 3 parts in 10,000 toward the red, which is what you would expect from a clock running about 3 parts in 10,000 slow. 8.5 light years from us, in a binary orbit with one of the most famous stars in the sky, sits a small dead star whose surface ticks measurably more slowly than ours, and whose light arrives reddened by exactly the amount its slowed clock implies. There are perhaps 10 billion white dwarfs scattered through our galaxy, the ash of dead stars from the past several billion years of cosmic history. Some sit in binary systems, like Sirius B. Others drift alone. All of them are slowly cooling, radiating away their stored heat into the dark, fading over hundreds of billions of years toward the eventual state of inert cold matter. While they cool, every one of them is keeping its own time, set by the gravitational depth of its surface. The white dwarf has aged less than the empty space around it, by a measurable amount every second, since the moment it first formed. Press further, and the universe holds something stranger still. A more massive star, one with a core heavier than about 1 4/10 times the mass of the Sun when fusion ends, cannot rest as a white dwarf. Electron pressure, the quantum mechanical effect that holds white dwarfs against their own gravity, fails at that mass, and the core collapses further. What stops the collapse, in the cases that have one, is a deeper kind of pressure. The electrons themselves are crushed into the atomic nuclei, where they merge with protons to become neutrons, and the result is an object made almost entirely of neutrons packed against one another at nuclear density. This is called a neutron star. A neutron star contains about 1.5 to 2 times the mass of the Sun, in a sphere only about 20 kilometers across, the size of a city. The density is harder to imagine. A teaspoonful of neutron star matter would weigh as much as a mountain. The surface gravity, where the thin crust of normal atomic matter sits on the neutron sea below, is something like 200 billion times the surface gravity of the Earth. Time at the surface of a neutron star runs slow against time far away by something like 20 to 30%. This is no longer a small effect. A clock placed on the surface of a typical neutron star would tick at about 3/4 the rate of a clock placed far above it. Over the course of a year, far from the star, only about 9 months would pass on its surface. The surface itself is a place of unimaginable extremes. The crust of a neutron star is a solid lattice of atomic nuclei jammed together at densities approaching that of an atomic nucleus, with electrons flowing freely through the gaps as a quantum fluid. The strongest mountains that could ever form on such a surface, against such crushing gravity, would be at most a few millimeters high. The magnetic fields of many neutron stars exceed 1 trillion times the strength of the strongest sustained magnetic fields produced in any laboratory on Earth. A particular class of neutron stars called magnetars carries fields up to 1,000 times stronger still, fields so intense that they would distort the structure of an atom from many kilometers away. Standing on the surface of any of these objects, even ignoring the gravity, would not be possible for any chemistry we recognize. Every atom in a human body would be torn apart by the magnetic forces alone, long before the gravity had time to crush it into a millimeter-thick film. The neutron stars we know of include some of the most extraordinary objects in astronomy. Many of them spin. The collapse that forms them concentrates their rotation in the same way a spinning ice skater pulling her arms and turns faster, and a neutron star can end up rotating hundreds of times per second. Many also carry enormous magnetic fields, the magnetic field of the original star concentrated into the much smaller volume of the remnant. When the magnetic axis of a spinning neutron star is offset from its rotational axis, it sweeps a narrow beam of radio waves around the sky like a lighthouse, and if the Earth happens to lie in the path of that beam, we see a regular pulse of radio waves once per rotation. Such an object is called a pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell, then a graduate student at Cambridge, working through the printout of a radio telescope. She found a faint signal that pulsed every 1.33 seconds with extraordinary regularity. Her supervisor briefly entertained, half seriously, that the signal might come from another civilization, given how artificial it looked. It turned out to be a spinning neutron star, and the discovery opened a new branch of astronomy. There are now thousands of known pulsars in our galaxy. Some rotate slowly, with periods of seconds. The fastest known, called millisecond pulsars, spin hundreds of times per second. This makes them extraordinary clocks. A pulsar that has spun stably for millions of years can keep time more precisely than any clock humans have ever built. The pulses come at a rate that is so regular and so resistant to outside disturbance that pulsars are routinely used as natural reference clocks for astronomical measurements. We have measured the period of the most stable pulsars to better than 1 part in 10 to the 15th, comparable to the best atomic clocks. They are, in effect, gigantic atomic timekeepers, spinning silently in deep space, ticking away the cosmic seconds with a fidelity that took centuries of human work to match in the laboratory. But pulsar clocks do not agree with our clocks. They tick at their own rate, and we have to correct for the gravitational slowing of their surfaces and for the velocity of their motion when comparing them to clocks on the Earth. A pulsar spinning at the surface of a neutron star is doing two things at once, by relativity. It is running slow because it sits deep in a gravitational well. It is also running slow because its outer surface is moving at relativistic speeds. For the fastest millisecond pulsars, the equatorial surface moves at 15% of the speed of light or more. Both effects combine to make the pulsar's intrinsic clock measurably different from any clock on the ground. The strangest demonstration of this came in 1974, when the radio astronomers Russell Hulse and Joseph Taylor discovered a pulsar in a tight binary orbit with another neutron star. The two stars circle each other every 7 hours and 45 minutes, at speeds reaching 0.3% of the speed of light. in an orbit only about 3 light seconds across. Hulse and Taylor watched the pulsar over years, using its precise pulse rate as a clock to measure the orbit, and they were able to confirm a long list of relativistic effects. The orbit precessed, in the same way Mercury's orbit precesses around the Sun, but enormously faster, by 4 degrees per year. The pulses were delayed and advanced by the changing gravitational time dilation as the pulsar moved through different depths in its companion's gravity well. And, most strikingly, the orbit slowly tightened by an amount that exactly matched the loss of energy by gravitational waves predicted by general relativity. The binary pulsar gave the first indirect evidence that gravitational waves existed, decades before LIGO measured them directly. Hulse and Taylor received the Nobel Prize for this work in 1993. The Hulse-Taylor binary is, in effect, a relativistic laboratory in space. 2 atomic clock-grade objects circle each other in a tightly curved region of space-time, and every effect that general relativity predicts can be watched playing out in real time, recorded as variations in the radio pulses that reach the Earth. Time, at the location of the pulsar, is doing many things at once. It is slowed by the surface gravity of the neutron star. It is slowed by the orbital motion. It is shifted periodically by the changing depth of the gravitational potential as the orbit ranges from near approach to far. And the orbit itself is losing energy to gravitational waves, which means the 2 stars are spiraling slowly together, and the space-time around them is gradually changing as a result. All of this is happening 21,000 light-years from us, and we watch it as a series of subtle modulations in a regular pulse arriving at our radio telescopes. This is what time looks like near a collapsed star. The clocks are dramatically different from ours. The differences are enormous by everyday standards, and yet the underlying physics is the same physics we use to correct the GPS satellites overhead. Push the equations a little further, into the region where the gravity becomes so strong that even neutron pressure fails to halt the collapse, and the picture becomes stranger still. The clocks of the surrounding region begin to slow toward 0. The light from anything falling inward reddens toward infinity. The very idea of the inside, as a region anyone outside can see or visit, breaks down entirely. To follow what time is doing there, we have to look at the place where the slowing is no longer a fraction. It is a stop. A black hole is what happens when collapse runs out of floors. The core of a star heavier than about 2 or 3 solar masses, when its fuel ends and its neutron pressure fails, has nothing left to stop it. It contracts past its own gravitational radius, vanishes from view, and continues to collapse with no remaining force in physics capable of halting it. What remains behind from the outside is a region of space whose curvature is so extreme that nothing crossing inward can ever come back out. Not matter, not light. The valley has become a shaft. The visible boundary of the shaft is called the event horizon. Inside it, all paths lead inward. The size of the horizon is set entirely by the mass within. A black hole of 10 solar masses, the kind formed by the death of a single very massive star, has a horizon about 60 kilometers across, the size of a small city. The supermassive black hole at the center of our own galaxy, 4 million solar masses, has a horizon about 24 million kilometers across, smaller than the orbit of Mercury. The largest known supermassive black holes in the centers of giant galaxies have horizons billions of kilometers across, larger than our entire solar system. In every case, the horizon is the surface beyond which time, as seen from outside, begins to behave in ways that border on the impossible. To understand what happens to a clock near the horizon, imagine lowering one very slowly toward it, by an unreasonably strong cable held by an observer at a safe distance. As the clock descends, it sinks deeper into the gravitational well of the black hole, And by the rule we have been following throughout this video, its rate of ticking, as seen by the distant observer, slows. The slowing is gentle at first, when the clock is still far above the horizon. As the clock approaches more closely, the slowing becomes severe. By the time the clock is just above the horizon, it is ticking so slowly that minutes on the clock correspond to years for the distant observer. As it nears the horizon itself, the slowing tends toward infinity. A clock placed exactly on the event horizon, as viewed from outside, never ticks at all. Time, on the boundary, has stopped. Now do not lower the clock by cable. Drop it. Let it fall freely toward the black hole. From the distant observer's point of view, the falling clock approaches the horizon ever more slowly, its rate of ticking dropping toward zero. The image of it reddening and dimming as the gravitational redshift carries its light into longer and longer wavelengths. It never quite reaches the horizon. From outside, the clock asymptotes onto the boundary, taking infinite time to arrive there, while its image fades into invisibility. This is why early German theorists called black holes frozen stars. From outside, the collapse that formed them never quite finished, and the surface of the collapsing matter still hangs, frozen, just above the horizon, by the infinite slowing of its time. From the clock's own point of view, however, nothing of the kind happens. The clock falls smoothly through the horizon at a definite moment by its own time, and continues to fall inward toward the center. From the clock's perspective, there is no infinite delay, no fade to red, no frozen surface. The clock simply crosses a boundary it cannot see, the way a swimmer crosses an arbitrary line painted on the bottom of a pool. Looking forward, it sees the center of the black hole, the singularity. Looking backward, it sees the universe outside, distorted by the gravity it has just passed through. The fall continues. The clock's own internal time, ticking at its usual rate, brings it to the center in a short while. By the standards of any object falling into anything stellar in scale. Both descriptions are correct. The distant observer sees the clock take forever to arrive. The clock itself arrives in seconds. Einstein's theory provides no privileged perspective from which to declare one truer than the other. The principle from earlier still holds here, only in its most extreme form. Two observers separated by a strong enough gravitational field will not agree at all about how long an event took, and both will be right in their own frame. The black hole is the most extreme illustration of this principle that the universe contains. The distant observer's time and the falling clock's time, in the vicinity of the horizon, diverge without limit. There is no fact of the matter in the cosmos about how long the collapse of any black hole has really taken. This has a consequence that bears thinking about. Every black hole we see in the sky is, from our point of view, still collapsing. The supermassive black hole at the center of M87, the one photographed by the Event Horizon Telescope in 2019, has been collapsing in our view since the original galaxy first formed, more than 10 billion years ago. From outside, the material that formed it is still falling in, asymptotically approaching the horizon, never quite arriving. From the inside, of course, the collapse finished long ago. The two pictures are not reconcilable from any single perspective, and the universe does not offer one. The black hole at the center of our own galaxy is closer to us, about 26,000 light-years away, in the direction of the constellation Sagittarius. It is called Sagittarius A, written with a small star symbol astronomers use for the central object of a galaxy, to distinguish it from the surrounding region. Its mass is about 4 million times that of the Sun. Its horizon is about 24 million kilometers across, 12 million from center to edge. It is, on the scale of supermassive black holes, modest. The Event Horizon Telescope photographed it in 2022 3 years after they had photographed the much larger one in M87. The two images look remarkably similar, a ring of light wrapped around a circle of pure darkness, scaled differently, but recognizably the same kind of object. What gives Sagittarius A away, more than anything else, is the motion of the stars near it. A swarm of about 100 massive young stars orbits within a few light days of the central source, in tight loops that take only decades to complete. The brightest and most carefully tracked is a star designated S2, a hot blue star about 15 times the mass of the Sun, on an orbit that brings it within a few light hours of Sagittarius A at its closest approach, called pericenter. At pericenter, S2 travels at over 7,000 kilometers per second, more than 2% of the speed of light, the fastest motion ever measured for a star bound to another body. It completes one orbit every 16 years. Two competing teams of astronomers have been tracking S2 since the early 1990s. One was led by Reinhard Genzel of the Max Planck Institute, the other by Andrea Ghez of UCLA. They received the Nobel Prize in 2020 for this work, jointly with Roger Penrose. What their measurements showed, beyond confirming the central black hole's mass and size, was that S2's orbit was not a closed ellipse. It precessed, the same way Mercury's orbit precesses around the Sun, but by many degrees per orbit rather than 43 seconds of arc per century. The precession is a direct consequence of the warping of spacetime around Sagittarius A, and its rate exactly matches general relativity's prediction. At pericenter, the time dilation of S2 itself, owing to its speed and its depth in the gravitational well, is large enough to shift the colors of its light measurably. The teams observed the predicted redshift in 2018 when S2 made its closest approach, and the shift was exactly what Einstein's theory had said it would be. Stand back for a moment and notice what this means. A star, about 15 times the mass of the Sun, is orbiting an object so compact that all 4 million solar masses of it fit inside a region smaller than the orbit of Pluto. The star sweeps in close enough to fall measurably deeper into the gravitational well at pericenter, and its clock visibly slows by the amount the theory specifies. We can see this happening. The light from S2, when it reaches us across 26,000 light-years, carries in its colors the imprint of the time dilation it experienced as it whipped past the black hole. We are watching, from one side of the galaxy, the slowing of time near the supermassive black hole at the heart of our own. Closer to Sagittarius A than S2 ever comes, the inside of the accretion flow swirls around the horizon. Material falling toward the black hole from the surrounding region piles into a flat rotating disk, heated by friction as it spirals inward. The innermost edge of this disk sits at the innermost stable orbit, about 3 Schwarzschild radii from the center for a non-rotating black hole, somewhat closer for a spinning one. Material crossing inside that radius can no longer orbit. It spirals inward, falls through the horizon, and is gone. The disk is what shines in the photographs, the bright ring of light surrounding the dark central shadow. Each photon in that ring was emitted by a small parcel of gas, whose own clock was running, at the moment of emission, at a rate substantially slower than ours. The light has climbed up out of the gravitational well to reach us, redder and dimmer than it left, like the light of the Sun, but much more so. It is worth dwelling on what this means about the photographs themselves. The image of M87, the ring of orange light wrapped around a circle of darkness, is a portrait of a region in which time is doing extraordinary things. The light forming the bright side of the ring is photons emitted from gas that was, at the moment of emission, deep in a gravitational well that slowed its clocks to a fraction of hours, and that was also moving at a substantial fraction of the speed of light around the central object. Both effects combine to alter the colors and brightness of the light that eventually reach the telescopes on Earth. The asymmetry of the ring, brighter on one side and dimmer on the other, is the visible signature of the gas on one side rushing toward us at relativistic speed and the gas on the other side rushing away, a Doppler-like brightening and dimming that is itself a direct consequence of relativistic motion in a curved spacetime. The dark shadow inside the ring is the projection of the event horizon, magnified by the bending of light through the surrounding curved space. To look at the photograph is to look at time at its most strangely behaved, 55 million light years from us, recorded as a particular pattern of brightness on the sky. For the largest black holes, the tidal forces at the horizon are gentle enough that an astronaut could, in principle, fall through one without immediately being torn apart. The horizon of the central black hole in M87, 6.5 billion solar masses, is so vast that the gravity changes only gradually across the body of any falling object. An astronaut crossing it would notice nothing in particular at the moment of crossing. They would continue to fall, looking outward at a universe whose light was compressing and blue shifting into a bright spot behind them, while the way back became, in a manner difficult to translate into ordinary language, simply unavailable. The direction we ordinarily call the future would now point inward. They would still have a future. It would merely all happen at the center of the black hole. For a stellar mass black hole, the situation is more violent. The horizon of a 10 solar mass black hole is only about 60 kilometers across, and the gravitational field changes so steeply across a human body that the difference in pull between head and feet, where one falling head first, would be enormous. Long before reaching the horizon, the tidal forces would stretch the falling person into a thin filament. The American physicist Kip Thorne coined a half-comical name for this, spaghettification, and the term has stuck because the geometry is exactly that. The clock would still pass through the horizon in its own time. It would simply do so in a less recognizable form. The crucial point, for the purposes of this video, is that the clock crossed the horizon by its own time, while from the outside the crossing took forever. Time, near a black hole, becomes more than just slow. It becomes a quantity about which observers in different positions cannot agree at all. Some events happen here in finite time and never happen there, even though both observers are watching the same physical situation. We have now traveled from the surface of the Earth, through the solar system, past dead stars, and to the edge of where time stops. But we have not yet looked at the largest scales of all. The universe itself, as a whole, has been expanding for nearly 14 billion years, and that expansion has consequences for time across cosmic distances that are, in some respects, even stranger than what happens at a horizon. The light reaching us from the most distant galaxies has been climbing through an expanding universe for so long that the very seconds of the events we are watching have stretched as their light crossed the void. To see what this means, we have to step back from any one place and look at time across the whole cosmos. Step back now, from any one place in the cosmos. Stop thinking about clocks lowered toward horizons, stars whipping around invisible centers, satellites overhead. Take in instead the whole universe at once. It is a region of space about 93 billion light-years across, containing perhaps 2 trillion galaxies, each of those galaxies containing on average 100 billion stars. It has existed for nearly 14 billion years, expanding the whole time, and every point in it is on its own clock, ticking at its own rate, set not just by local gravity and motion, but by where it sits in a universe that is itself growing. The expansion is the central fact here. In 1929, the American astronomer Edwin Hubble, working at the Mount Wilson Observatory in California, published a paper showing that the light from distant galaxies arrives at the Earth shifted toward longer wavelengths, and that the shift was larger for more distant galaxies. The natural interpretation, suggested by the Belgian priest and physicist Georges Lemaitre a few years earlier on theoretical grounds, was that the galaxies were receding from us, and that the universe itself was expanding. Every galaxy was moving away from every other galaxy. Not because they were flying outward through pre-existing space, but because the space between them was in some sense getting larger. This sounds like a metaphor, but it is not one. Einstein's general relativity, taken as a complete description of how gravity and geometry behave in the universe at large, has solutions in which the geometry of space itself changes with time. Lemaitre and the Russian mathematician Alexander Friedman independently found these solutions in the 1920s, and they describe a universe in which the distance between any 2 points not bound together by gravity grows in proportion to a single time-dependent factor called the scale factor. As the scale factor grows, all unbound distances grow with it. Nearby galaxies that are gravitationally bound, like the Andromeda Galaxy and our own Milky Way, are not carried apart by this expansion. But galaxies far enough away that no gravitational connection holds them to us, which is the vast majority of them, are receding, and at a rate that increases with distance. What this means for time is striking. A photon of light emitted by a distant galaxy on its long journey toward us is traveling through a universe that is itself expanding while the journey is in progress. The wavelength of the photon, which is in effect a small distance between two crests of an electromagnetic wave, expands along with the space the photon is traveling through. By the time the photon arrives at our telescopes, its wavelength has been stretched in proportion to how much the universe has expanded since the photon was emitted. We see the photon at a longer wavelength than it was emitted, which is to say redder. This is called cosmological redshift, and it is a third kind of shift in light, distinct from the velocity-based Doppler shift we know from ordinary motion and from the gravitational redshift we have seen near massive objects. The cosmological shift is not caused by either of those. It is caused by the expansion of the universe itself, operating on the photon while it travels. A galaxy at a redshift of 1, which corresponds to a distance of about 8 billion light-years, has its light stretched to twice the wavelength at which it was emitted. A galaxy at a redshift of 2 has its light stretched to 3 times the original wavelength. The most distant galaxies, confirmed by the James Webb Space Telescope at redshifts of 10 or more, have their light stretched to more than 11 times the wavelength at emission. Ultraviolet light, the brightest emission of young hot stars, arrives at our telescopes as infrared. The visible universe of those galaxies, as it appeared to its own inhabitants if any existed, is invisible to us in optical light. We see them only at wavelengths that no eye made for visible light could detect. It is worth being precise about what kind of stretching this is, because the natural first instinct is to treat it as a Doppler effect, the same kind of shift you hear in the pitch of an ambulance siren as it passes. The cosmological redshift looks superficially like a Doppler shift, but it is not one. A Doppler shift requires the source and the observer to be moving relative to each other through some shared space, and the size of the shift depends on their relative speed. The cosmological shift does not work that way. The galaxies are not, strictly speaking, moving through space at the speeds their redshifts would imply. They are sitting more or less in place, in regions of space that are themselves carrying them apart from one another as the geometry of the whole universe expands. For distant enough galaxies, the implied recession speed exceeds the speed of light, which would be impossible if the galaxies were truly moving through space, but is perfectly allowed when the space between them is expanding. Light from those galaxies is not being chased by the expansion. It is, in a sense, swimming against a current that is carrying its source ever further from us with each year that passes. The redshift comes not from the source's motion, but from the lengthening of the photon's path during transit. The universe is the thing that is changing, not the things in it. Now here's the part that bears directly on this video. The same stretching that affects the wavelength of light also affects the rate at which events appear to happen in distant galaxies. Imagine a distant galaxy in which a star explodes, and the explosion lasts, by the galaxy's own clock, 20 days from first brightening to fading away. The light from the explosion, the entire 20 days of it, travels toward us through the expanding universe. By the time it arrives, the photons emitted at the start of the explosion have had a longer time to reach us than the photons emitted at the end, because the universe has expanded during the interval. The result is that the explosion, as we see it, appears to last longer than 20 days. The whole light curve, the rising brightness and slow fading of the supernova, has been stretched in time in proportion to the same factor by which the wavelength was stretched. This effect is called time dilation of cosmological events, and it has been measured directly. The cleanest measurements use a particular kind of supernova called a Type 1a, which results from the thermonuclear explosion of a white dwarf that has gained too much mass from a companion. Type 1. A supernovae have light curves that follow a characteristic shape, rising over a couple of weeks and then declining over several months in a way that is consistent enough across the cosmos that they can be used as standardized distance markers. Astronomers have observed thousands of these supernovae across a wide range of distances. The light curves of the nearby ones, in galaxies at low redshift, follow the standard shape over the standard timescale. The light curves of the distant ones, in galaxies at higher redshift, follow the same shape over a longer timescale, stretched by exactly the factor predicted by the cosmological expansion. A supernova at a redshift of 1 takes twice as long to brighten and fade, as we see it, as one nearby. A supernova at a redshift of 2 takes 3 times as long. The pattern was confirmed by the early 2000s in data sets large enough to leave no doubt. What this means, when you let yourself feel it, is unusual. We are watching, in slow motion, the explosions of stars that died billions of years ago. The light curve of a Type 1a supernova at a redshift of 1 unfolds in our telescopes over 40 days instead of 20. Because the entire event, from the perspective of the universe between us and it, has been stretched in time by the expansion. The star exploded once, in its own galaxy, in its own seconds. Those seconds reach us as 2 seconds each. The supernova's clock and our clock disagree about how long the explosion lasted, by a factor that depends on how long the light has been traveling, which is to say on how much the universe expanded during the journey. The effect operates on everything, not just supernovae. Anything happening in a distant galaxy is, from our perspective, occurring at a rate slower than it occurs locally. The rotations of distant galaxies, if we could measure them in real time over astronomical durations, would appear to proceed in slow motion. The bursts of energy from distant quasars are stretched in arrival by the same factor that stretched their light. The gravitational waves now being detected by LIGO from the mergers of black holes in distant galaxies arrive at us stretched in frequency, lower pitch than they were emitted, in exactly the same proportion. The expansion of the universe, as a phenomenon, applies an inseparable time dilation to every cosmic event we observe across cosmic distances. There is something quietly destabilizing about this when one first absorbs it. We have spent the previous sections of this video looking at how local conditions, gravity, and motion stretch time. Now the universe itself, just by being large and expanding, is stretching time across cosmic distances. The two effects compound. The light from a distant galaxy is being slowed by the gravity of every massive object it passes near, by the motion of its source, and by the expansion of the universe through which it travels. Every photon arriving at every telescope on Earth, from any source farther than a few hundred light years away, has been continuously modified in arrival rate by some combination of these factors during its journey. Consider what we are looking at on a clear night when we point a telescope toward a distant galaxy. The light we see in the eyepiece was emitted on the galaxy's own clock some long time ago. For Andromeda, the nearest large galaxy to ours, the light is about 2.5 million years old. For the Coma cluster, 300 million. For a galaxy at redshift 1, 8 billion years. for the most distant galaxies the Webb telescope has identified, 13 billion years and more. We are not seeing those galaxies as they are now. We are seeing them as they were when their light was emitted. And as we look at increasingly distant galaxies, we are looking at increasingly older snapshots of the universe, frozen in mid-event, their light slowed and reddened in arrival by the expansion of the space between us. This is what astronomers mean when they say that telescopes are time machines. They mean it literally, not as a figure of speech. To look at the Crab Nebula, the remnant of a supernova that exploded about 1,000 years ago, is to see what was happening in a particular small region of our galaxy a millennium back. To look at the Andromeda Galaxy is to see what was happening in our nearest galactic neighbor when our hominin ancestors were just beginning to walk on two legs. To look at a galaxy at redshift 1 is to see what was happening in the universe when it was half its current age. To look at the most distant galaxies is to see the universe when it was just over 400 million years old, less than 3% of its current age. And every one of these glimpses arrives stretched in time by the expansion of the universe between us. The stars in those distant galaxies were not orbiting their galactic centers in slow motion. The supernova were not exploding in slow motion. The gas was not falling toward central black holes in slow motion. They were doing all of these things at the usual speeds, by their own clocks. It is the universe between us and them that has stretched their seconds into longer seconds, by virtue of the expansion that happened during the photon's journey. There is no privileged perspective in this either. An astronomer in one of those distant galaxies, looking back toward our Milky Way, would see our supernovae, our quasars, our gravitational wave events stretched in the same proportion by exactly the same factor. The expansion is symmetric. We are as distant from them in their telescopes as they are from ours. Every galaxy in the universe, looking outward at every other galaxy, sees the rest of the cosmos receding and the events on it slowing down in proportion to distance. There is no center to the expansion, no special place where the universe is at rest. There is only the geometry of the whole, and the clocks scattered through it, each ticking at its own rate, and the photons traveling between them, carrying news that arrives stretched in proportion to the journey. The farthest light we have been able to see, however, is older than any galaxy. It comes from a moment before any galaxies existed at all, from the time when the universe was so hot and dense that ordinary matter could not yet form. That light has been traveling toward us for nearly the entire age of the universe, and it has been stretched by the cumulative expansion of all those years by a factor of more than 1,000. To follow this story to its end, we have to look at the most red-shifted, most stretched, oldest light in the cosmos. It is called the cosmic microwave background, and it is, in a strict sense, light from the beginning of the visible universe. The light from the cosmic microwave background fills the sky. It is everywhere at once. In every direction one might point a sensitive enough antenna, with very nearly the same brightness. It was discovered, almost by accident, in 1964 by two engineers at Bell Laboratories named Arno Penzias and Robert Wilson. They were trying to calibrate a large horn antenna for radio astronomy in Holmdel, New Jersey, and they kept finding a faint background hiss they could not eliminate. They cleaned the antenna, they checked the wiring, they evicted a pair of pigeons that had been roosting inside the horn, scrubbed out what the pigeons had left behind, and tried again. The hiss was still there. It was the same in every direction they pointed the antenna. After exhausting all the more plausible explanations, they realized, with the help of theorists at nearby Princeton University who had been predicting just such a signal, that they were detecting the relic radiation of the early universe, light from a moment some 380,000 years after the Big Bang itself, when the universe first became transparent. Penzias and Wilson received the Nobel Prize in 1978 for the discovery. To understand what this light is, and what it tells us about time, we have to picture the early universe briefly. In the first few minutes after the Big Bang, the entire universe was so hot and dense that protons and electrons could not bind into atoms. They moved freely through space as a kind of charged fog, and any photon of light that tried to travel through that fog would be scattered almost immediately by the free particles. The universe was opaque. There was no way for light to cross it. This continued for about 380,000 years, during which the universe expanded and cooled. At a temperature of about 3,000 degrees, cool enough for the first time, the protons and electrons could combine into neutral hydrogen atoms, and the fog cleared. Suddenly the photons could travel freely, and the universe became transparent. The photons that had been bouncing around in the fog now streamed outward, each one beginning its long journey through whatever space lay ahead of it. Those photons, the ones that happen to be reaching us right now, have been traveling for nearly 14 billion years, the entire age of the universe minus those first 380,000 years. They are not, when they arrive, what they were when they began. The light was emitted at a temperature of about 3,000 degrees, hot enough that the spectrum peaked in the visible band, the same band our eyes evolved to see. By the time it reaches us, after nearly 14 billion years of travel through an expanding universe, the wavelength has been stretched by a factor of about 1100. The visible photons have become microwave photons, with wavelengths around a millimeter, and the temperature has dropped from 3,000 degrees to about 2 7/10 degrees above absolute zero. The same light, the same photons, the same total energy redistributed across a longer wavelength. The universe has, through expansion, cooled what was once a bright, hot fog into the faint, cold whisper that fills the modern sky. The cosmic microwave background, then, is light from a moment we can almost name. The universe was 380,000 years old when those photons last interacted with matter. Everything they have done since is to stream through an expanding universe, becoming redder and dimmer and slower with every passing year. They are the oldest light there is to see. There is no earlier light available, because the universe before 380,000 years was opaque to its own radiation. The cosmic microwave background marks the boundary of what we can observe with light, in the same way the horizon of a black hole marks the boundary beyond which light cannot escape. Now consider what this means for time. The photons arriving at our microwave antennas today were emitted when the universe was only 380,000 years old. The events that produced those photons, the last scatterings of light off newly forming hydrogen atoms, happened at a time when the universe was 1,000 times smaller than it is now. The light has been stretched by exactly that factor. Anything that was happening at the moment of emission, any process, any oscillation, any flicker, would now appear to us as occurring 1,000 times more slowly by the cosmological stretching of time we walked through in the previous section. The early universe is, in a strict sense, accessible to us, but it is accessible only in extreme slow motion, with all of its events stretched in arrival by a factor of more than 1,000. There are subtle structures in the cosmic microwave background, small variations in temperature from one patch of sky to another, that carry information about the conditions of the early universe. Sound waves rippling through the hot fog left their imprint in the distribution of these patches, the tiny hot and cold spots that satellites like COBE and WMAP and Planck have mapped over the past few decades. From those maps, cosmologists have been able to reconstruct the age, the composition, and the geometry of the universe to remarkable precision. The age of the universe, 13.8 billion years, is known to a few tens of millions of years from these maps. The temperature of the cosmic microwave background, 2.725 Kelvin, is measured to better than 1/100th of a degree across the sky. The structure visible in those maps, frozen as a still photograph from 380,000 years after the beginning, is a snapshot of a moment when time itself was running. by our accounting, 1,000 times faster than it is now in those regions. It is worth pausing on what those patterns of hot and cold spots actually represent. In the hot fog of the early universe, before atoms could form, regions of slightly higher density would attract more matter by gravity, and the increased pressure would push the matter back outward, in oscillations that propagated through the fog as sound waves, in the most literal sense. The early universe had a sound, made of pressure waves moving through ionized hydrogen, and those waves had a characteristic wavelength set by the speed of sound in that medium and the time available for them to ring. When the fog cleared and the universe became transparent, the pressure-driven oscillations froze in place. The hot and cold spots we see in the cosmic microwave background today are the final positions of those frozen sound waves, the silent ghost of an early universe music recorded directly into the geometry of space. The pattern of those frozen waves became, over billions of years, the seeds around which all the structure of the modern universe condensed. Every galaxy in the sky tonight grew, ultimately, around the gravitational potential of one of those slightly denser spots. The map of the cosmic microwave background is, in a strict sense, the prenatal portrait of every galaxy we can see. Here is where the strangeness sharpens. We have been talking about light from the early universe arriving at us slowed down by expansion. But the regions of space we are seeing in the cosmic microwave background, the patches of fog that emitted those photons, did not stay where they were. They have continued to age on their own clocks, while their light has been traveling toward us. The regions we are watching in the photograph of the early universe, drawn by the microwave background, are now, in their own time, almost 14 billion years old. They have become galaxies, presumably, or collections of galaxies. They have evolved through the same cosmic history we have. What we are seeing in our sky tonight is light they emitted when they were newborn, but they themselves, in their own present, are as old as we are. This means there is something genuinely paradoxical about asking what time it is right now in the most distant regions visible in the cosmic microwave background. The cosmic time of those regions is the same as ours because the universe has expanded uniformly, but the light arriving from them is light from their own past. From our point of view, we are seeing them at a time when they were 380,000 years old. From their own point of view, they are now 14 billion years old, just like the regions around us. There is no observer in the universe with the privileged perspective from which both pictures can be reconciled. Every observer, anywhere in the universe, sees themselves as currently in the present and sees the rest of the cosmos in various stages of its past, in proportion to distance. This is what cosmologists mean when they say the universe has no single now. There is no master moment, shared by every region, that anyone could legitimately call the universal present. There is only the local present of each region, with the regions communicating with one another at the speed of light, which means every message any region sends to any other arrives carrying news from that region's past. The cosmos is a kind of vast extended conversation in which everyone is replying to messages from years or millennia or billions of years ago, and the messages they themselves send out today will not reach distant observers for an equally long time. There is no shared moment to be in. There are only the personal clocks of every region, ticking in their own places, exchanging delayed information. The depth of this strangeness becomes vivid when one considers the regions of the universe so distant that their light has not yet reached us and will not reach us for billions of years more. Those regions exist now. They are, by all of our best theory, exactly as real as the regions we can see. The light from them will arrive someday, carrying news of what was happening when their photons set out, and the news will arrive stretched in time by an even larger factor than the cosmic microwave background. We will see them, eventually, in even slower motion than the early universe we see today. By the time we do, billions of years will have passed in our own region. the universe will have continued to expand. Our clocks will have kept ticking, and the messages we receive will tell us only about how those distant regions were when our slow correspondence first crossed the gap. There are limits to what we will ever see. The expansion of the universe is, by recent measurement, accelerating. There is some force, called dark energy for lack of a better name, that is pushing space apart faster and faster. The consequence is that regions of the universe beyond a certain distance, called the cosmic event horizon, are receding from us faster than the speed of light, and their light, even if emitted toward us today, will never reach us. Those regions are not unreachable in principle. They are unreachable in practice because the space between us is growing faster than light can cross it. Their clocks are still ticking. They are still part of the universe. But we will never receive a signal from them again, and we will never know what they look like, except by extrapolation from the parts we can still see. This means the universe has, in a sense, no single observable present at all. We see only a sphere of the cosmos around us, bounded by how far light has had time to travel since the beginning. The sphere will grow slowly as more time passes. But in the very long future, as the expansion accelerates, the visible universe will actually shrink, in terms of what new information can reach us. Distant galaxies will redshift out of detectability, one by one, as their light is stretched past the limits of what any conceivable instrument could capture. The cosmic microwave background will continue to redshift toward longer and longer wavelengths until eventually, billions of years from now, it will become so faint and so cold that it can no longer be measured. The universe will hide its own beginning from any observer who watches long enough. For now, though, we still see it. We can still measure the cold whisper of light from 380,000 years after the Big Bang. We can still observe distant supernovae stretched in time by the expansion. We can still time the precession of S2's orbit around the central black hole and compare it to general relativity. We can still synchronize the satellites overhead. We can still notice, with the most precise of our atomic clocks, the difference in time between the top and bottom of a book on a tabletop. The universe, in our particular slice of it, in our particular century, is still letting us see the structure of time it actually has. What we have seen, by the journey through this video, is that there is no single thing called time at all. There is only the time of each place, each motion, each depth in each gravity well, woven together by Einstein's geometry into the fabric of a universe that is itself expanding. Every clock in the universe is on its own, and every clock is correct in its own frame, and no two of them ever quite agree. The intuition we all carry, that a moment in one place is the same moment as in any other, is one of the most deeply embedded illusions of human experience, and one of the first. The universe gives up the moment any precise instrument is brought to bear on it. To see that, in the small and the vast, has been the work of this video. Return to where this video began. Wherever you are sitting or standing, whatever room or street or train carriage holds you right now, your own clock is still ticking. It has been ticking through everything we have looked at, through the climb up out of the Earth's gravity well to the satellites overhead, through the long descent into the sun and out past the planets and the dead stars, through the slow approach to the horizons of black holes, through the great expanding distances to the cosmic microwave background. None of that has stopped your own time. It has continued second by second, at whatever rate the local geometry of space-time sets for you, in the small and particular region of the universe you happen to occupy. We are, all of us, on our own clocks. The clock on the satellite above us is on its own clock. The astronauts on the orbiting station are on their own clocks. The probes in the outer solar system, the rovers on Mars, the pulsars in the disk of our galaxy, the star S2 racing around Sagittarius A, the photons in the disk of the supermassive black hole at the heart of M87, the distant supernovae stretched in time by cosmic expansion, the cold whisper of the cosmic microwave background, the unreachable galaxies beyond our event horizon, all of them are on their own clocks. None of those clocks is synchronized with any other. None of them, by any honest accounting, agrees about what time it is. Each one ticks in its own place at the rate the local conditions allow. It is worth holding this for a moment because of how completely it contradicts the picture of time most of us grew up with. The intuition that time is something universal, that a moment in one place is the same moment as in any other place, that now is the same now everywhere, is so embedded in human language and human thought that it can feel almost beneath examination. To say that today is Tuesday is to imply that it is Tuesday everywhere, all at once, that the universe is currently in its Tuesday state. The universe does not actually behave that way. There is no Tuesday anywhere except in some particular place, on some particular clock, set by the geometry of where that clock sits and how it moves. This is not a small adjustment to the picture. It is the dissolution of one of the oldest assumptions in human thought. Every philosophical tradition that has worked out a metaphysics of time, from the ancient Greek to the medieval Christian to the early modern, has rested on the assumption that there is some shared moment in which everything that is happening is happening. The universe was supposed to have a single present, even if different observers might disagree about how to describe it or what to call it. Einstein's work, and the century of experimental confirmation since, has dissolved that assumption gently and completely. There is no shared present. There never was one. Every observer, anywhere, sits in their own present, and the connection to other observers' presence is mediated by light or by gravitational signals that take time to travel, and that arrive carrying news from the sender's pasts. The universe is, in this respect, profoundly local. Every clock is alone in its own present, and the rest of the universe is, from that clock's perspective, a tapestry of past moments arriving from different distances and different depths in different gravitational wells. The picture of time we have arrived at by the end of this video is something stranger and more local than the picture we started with. It is not a single river flowing from past to future, the same speed everywhere. It is a vast field of clocks scattered through the geometry of the universe, each one running at its own rate, each one correct in its own region, none of them able to settle a universal time. The river image is the wrong one. Imagine instead a great quiet ocean, with every drop of water carrying its own tiny clock, all of the clocks ticking at slightly different rates, and the rates set by the depth and motion of each particular drop. That is closer to the actual situation. The universe has not one time but many, woven together by Einstein's geometry into a single coherent fabric, in which every observer sees their own time as ordinary, and the times of distant places as shifted, stretched, slowed, or accelerated in proportion to the geometry between them. There is something quietly humbling in this, because of what it suggests about our own ordinary experience of time. We feel time passing at a particular rate, more or less steadily, throughout our lives. That feeling is accurate, but only locally. Our cells age at the rate the gravity and motion of our bodies allow, and we are not aware, from inside our own experience, of any of the deviations from a universal rate. We do not feel ourselves running slower than the satellites overhead. We do not feel ourselves running faster than the deep interior of the Earth. We do not feel that we have lived, over the course of our lives, about 1.5 seconds less than we would have in interstellar space. The feeling of time in our own bodies is simply the feeling of our own clocks, and our own clocks tell us nothing about how they compare to any other clock anywhere else. That comparison is something we have to compute, with instruments far more precise than our own subjective sense. And the answer the instruments give is always that no two clocks anywhere in the universe are running at exactly the same rate. In some sense, the entire history of physics on this question has been the slow uncovering of what was already there. The universe has presumably been operating this way since the beginning. The clocks have always run at their own rates. The light from distant galaxies has always arrived stretched in time. The horizons of black holes have always been places where time slows toward a stop. Nothing about this changed when Einstein wrote down his equations, or when atomic clocks became precise enough to measure the differences. What changed was only how much of it we could see. The universe was always doing all of this. We simply lacked the instruments to notice. The instruments we now have are extraordinary. Optical lattice clocks that can detect the warping of time across a single floor of a building. Radio telescopes that can extract the orbits of stars at the center of our galaxy from their motions over decades. The Event Horizon Telescope, which can photograph the shadow of a black hole 55 million light-years away. The Webb Space Telescope, which can capture infrared light from galaxies emitted when the universe was less than 5% of its current age. The LIGO interferometers, which can feel the ripples of black hole collisions a billion light-years away. The Planck satellite, which can map the temperature of the cosmic microwave background to better than 1/100th of a degree across the entire sky. With these instruments, we have built a picture of time across the universe that no previous generation could have imagined. And the picture is consistent in every detail we have been able to check with what a patent clerk in Bern proposed in 2 short papers in 1905 and 1915 on the basis of 2 simple thought experiments and a refusal to look away from what those experiments implied. There is something genuinely moving about how far this has come. Einstein, working in his small office in the patent office in Bern, looking out the window at the slow, steady motion of the clocks on the great clock tower across the square, thinking about a single peculiar fact about the speed of light, would have had no way to know that the equations he was writing would, a century later, be confirmed across the universe at every scale, from a tabletop to the cosmic microwave background. He worked from first principles, with nothing more than pencil, paper, and the kind of stubborn attention to small inconsistencies that the best science has always required. The universe, when we finally caught up with him, turned out to be exactly as he had said. The work that went into catching up was the work of generations. Telescopes had to be invented and reinvented. Atomic clocks had to be built, refined, networked, and synchronized. Rockets had to be lifted past the atmosphere. Satellites had to be placed in precise orbits. Particle accelerators had to be designed to push protons to within a hair of the speed of light. Radio dishes had to be linked across continents. Vacuum tunnels had to be built long enough and isolated enough to measure ripples in space smaller than a proton. Hundreds of thousands of scientists and engineers over more than a century contributed pieces of the apparatus that has, in the end, allowed us to look at the universe carefully enough to see what time is actually doing in it. The picture we now have did not emerge from a single mind or a single discovery. It emerged from the slow accumulation of careful work in laboratories and observatories and patent offices and clock rooms by people who chose the difficult questions and stayed with them. We do not yet have the full story. There are pieces of the picture that still resist understanding. The interior of a black hole beyond the horizon is described by Einstein's equations only at the cost of producing a singularity, a point where the math gives infinity and the physics breaks down. The marriage of general relativity with the quantum mechanics that governs the small remains an unsolved problem, and it is at the heart of the deepest open questions in modern physics. What time itself is, at the most fundamental level, may turn out to require concepts we do not yet possess. The picture we have walked through in this video is the picture of time as Einstein gave it to us, and as we have measured it. it is not, almost certainly, the complete picture. There will be more to learn and more to see in the coming century. For now, though, we have the picture we have. And the picture is enough to change how one walks through a room. The next time you stand up from a chair, your head is on a slightly faster clock than your feet. The next time you climb a flight of stairs, every step lifts you into a region of marginally faster time. The next time you look up at the sky on a clear night, every star you see is on its own clock, running at its own rate, sending you light that was emitted at some particular moment in its own past, and has been traveling toward you ever since, slowed and reddened and stretched in arrival by everything its photons crossed. There is no universal moment at which any of this is happening together. There is only your moment, here, in your room, on the clock of your own body, and the long-delayed correspondence with the rest of the cosmos. The phone in your pocket, sitting an arm's length below the watch on your wrist, is on a marginally slower clock than the watch. By the time you read this sentence, the two have drifted apart by an amount measured in attoseconds, less than a billionth of a second, over the course of a year of you carrying the same phone in the same way. The accumulated drift would be in the femtoseconds, still too small for any instrument in your pocket to measure, but now within the reach of a research laboratory clock. The pulse in your wrist, the breath in your chest, the firing of every neuron in your brain, the slow ticking of every cell as it ages and divides, are all happening at the rate of the local time around them, slightly different from the rate around the phone in your pocket, slightly different from the rate around the chandelier on the ceiling. We do not feel any of it. We are not built to feel it. But it is there, every second, in every body, on every floor of every building, on every continent of every planet. This is the world we live in. It is not a strange world. It is the world the universe has, the only world it has ever had, and the strangeness was only ever in our long failure to notice. To see it at last, in the small and the vast, in the wrist and the satellite, in the white dwarf and the cosmic microwave background, has been, in some quiet way, to come home to a place we had been living in all along without recognizing. If anything in this video has stayed with you, leave it a moment to settle before the next thing claims your attention. We will be back soon with another mystery from the sky.